Hello everyone, welcome to Dakshana E classroom program. So in the last lecture we saw how an inductor behave when it is connected across a battery or resistor when switch is closed. So initially at t is equal to 0 it behave like open circuit. It does not allow any current, is it? If already current was there, then it will not allow any change. Initially same current will flow. T equal to infinity, it just act like in a conducting wire, right? And we saw how growth and decay of current and like behavior of inductor. We saw some cases, some problem in last lecture. Let's see few more cases based on the concept, then we will see new like next concept. So here we have one problem. In the circuit shown in figure, switch S1 remain closed for a long time. So means this is switch S1 which remain closed for a long time, and S2 remain open. So this is open, so you can just see this circuit is of no use. Okay, now S2 is closed and S1 is open, and you're asked to find out di by dt just after this movement. This movement means when S1 is open and S2 is closed, that is movement. So just after that movement we are asked to find di by dt. Okay, so let's see how we can see. So first is when, let's say when S1 was closed for long time and S2 open, right? In this situation what will happen? This is simply no, like this circuit will be just like at after long time. Okay, the circuit will be, so I can write the current, let's say here I1 current, and it will be flowing this way, is it? So I can write here it will be after long time, it will be just like wire. So the current I can write I1 will be simply equal to E by R, current through inductor. So this much current will be flowing through the inductor initially. Clear? All right. Now next thing is, now at this moment this is open and that is closed. So after the movement of S2 closed, or I will write just after, is it? I should write it just after S2 closed and S1 opened. What will be the situation? The situation will be, this is inductor, this is the resistor, and battery this way. So this is 4E, this is L, 2R, and here current I will be flowing. Is it clear? Now here again what I can do is I can apply KVL in this. So here the current through this inductor, you can see it's flowing this way. So just after switch is S2 is closed, this current will not change, it will still flow this way. So current will be this still I1 and this way, and we know already I1 is equal to what? E by R. So now what I can do is I can apply KVL in this loop, apply KVL in loop. So now I can go from here. Now remember that I am going opposite direction of current, so that's why I will write here, so I am going this way, okay, in the loop. So opposite direction, then I will write plus dl di by dt, and here also current flowing this way, I am going opposite to that, so it will be plus 2r into I, and I is E by R, and then plus 4E equal to 0. I hope this is clear. Now I am going this way. You can go this way also, there is no problem, you will get exactly still same thing. So I am going this way, so now I am going in the direction opposite to the current, so that's why I will be like writing it plus L di by dt. Here also opposite to the direction of current, so it's plus 2R into I and plus 4E equal to 0, and this implies this is 6E, and this di by dt is coming out to be, RR gets cancelled, minus 6E by L. So this is the answer. So I hope you understood this problem. It's just one different model you should learn, like how we can approach in different like conditions for different problems, is it? Let's see another problem here. Okay, let's see another problem here. So initially switch 2 was kept closed for a long time. Now it is shifted to position 1 at t is equal to 0. After that, find I current in the inductor as function of time. So like initially I can write initially for long time. You can write S2 was closed, kept closed. So in this situation, S1 was open and the circuit was like this. S2 was kept closed. So what is E, L and R? So this is the circuit. So I can write I, right? I can write I. So I1 is equal to, let's say, E divided by R. It's 1 minus e raised to power minus T R by L. And at t equal to infinity, I can write, because it's kept closed for a long time, this I can write I1 is equal to I0 is equal to E by R. So this is the current flowing across resistor I0, is it, after a long time. At this moment, what is done? Switch is shifted to position 2. So switch is shifted to position 2, it's open. So circuit, I think you can easily imagine this will be the circuit. After that, inductor, resistor, R, L, and this is 3E. And remember here I0, its active inductor, is equal to E by R. So this is the situation here. Now at t is equal to 0. What I can do? Again we can apply KVL. Apply KVL in loop. So I can write 3e minus L di by dt minus IR equal to 0. Clear? And I is not 0 here at t is equal to 0. So this implies 3e minus 2IR equal to L di by dt can be rearranged di 3e minus 2IR equal to dt by L, integrating it 0 to t. 0 it's I0 to I, remember that. So integrating it, we are getting it's minus 1 2R ln 3e minus 2IR divided by 3e minus 2I0 into R equal to T by L. Just simplifying it further, so I am getting here, this is 3e minus 2IR divided by, if I am substituting here 3e minus 2I0 into R, I0 is E by R, so 2E by R, so it's 3E minus 2E means it's E divided by E, and this side it's we are getting minus 2RT by L, and rearranging it, so I am getting I is equal to E and taking it this side, so this is a 3e minus e raised to power minus 2RT by L and divided by, this is 2R, and this implies I is equal to E by 2R. It's 3 minus e raised to power 2RT by L, and this is the answer. Current in the circuit as function of time. So I think like now you should not have problem in solving circuit having inductor, resistor, and at any moment of time if it is asked, depending on what exactly it is given, you write the KVL, write the correct condition. You should know what will be the circuit, how an inductor will be behaving at what time t is equal to 0 or at t equal to infinity, and accordingly proceed it and get the answer. Okay, so this is all about like little bit some problem based on circuit analysis, for solving problems, solving circuits, finding current and so on, having like inductor in the element or inductor in the circuit. Let's see next topic for inductor. Okay, so the next is energy stored in an inductor. If I talk about an ideal inductor, then actually an ideal inductor is an energy storing device. It does not dissipate energy, any energy. If some resistance is there or inductor coil is also having some resistance, in that situation some heat loss will be there. Otherwise, in ideal inductor there is no loss of energy. So just consider here one situation. So here we have inductor. If it is connected across some battery, is it, let's say it's connected across some battery and the switch is closed at t equal to 0, we have seen the current through this inductor I, is it, I is equal to E by L into T. Clear? Or it increases with time, and this implies actually in terms of this I can write equal to E by L, right? Or we already know that phi is equal to Li, and this implies d phi by dt equal to L di by dt. Minus sign is just that it will be opposing, is it? Otherwise we can write this is the EMF across inductor. This can be written as L di by dt, magnitude of EMF. So now see here, across this inductor there is, depending on if it is like increasing, then polarity will be this, decreasing then it will be reverse. This battery having some EMF is continuously supplying some current, and across the inductor some current is flowing and potential difference is there. And you can see during charging, if I am saying like initially when current is increasing, is it, initially when current is increasing through inductor, then what is happening? This is the battery continuously supplying energy. Where it is going? Definitely it's storing in the inductor. Clear na? So we can write EMF is this, current is this, across this inductor is I, the power of power absorbed by inductor. This can be written as power is equal to what? I into EMF, that is equal to L di by dt. Clear? And this power is equal to what? Du by dt, energy, rate of energy stored. Clear? This is equal to, I can write du equal to L I di by dt. U means energy, so the rate of energy is changing, that is power, energy stored. This can be, this implies du equal to L I di. I can integrate it from 0 to I, then 0 to u, and solving we are getting u is equal to L I square by 2. So actually this is the energy stored in inductor. So when current I is flowing passing through the inductor, then energy stored in the inductor is given by Li square by 2. Is it clear? Simple thing. Here you can see battery is continuously supplying energy, and here inductor, it's like, see, positive terminal, negative terminal. So whenever energy is entering positive terminal, device act like an basically energy storing device, or like you can say resistor means it's consuming energy, but here consuming, it's not getting lost in the form of heat, it's storing actually, is it? So here in this situation, resistor are like the inductor acting like a load, but it's not dissipating energy. Remember that it's actually absorbing energy, or it's storing this much amount of energy. So energy stored in the inductor is given by this. I can write something else about this. So consider an inductor coil means one solenoid, is it? energy we got. So consider here a solenoid, consider a solenoid coil, right? So it's a area of cross section of coil, let's say A, length, let's say L, inductance L, capital L, L small l is the length, I is the current, then B magnetic field in the solenoid. If I current flow, let me write it capital I, in coil, then B magnetic field given mu naught into Ni, N number of turns per unit length. Clear? This is the situation. So energy stored in this is given by its L I square by 2, and we know L is equal to what? Mu naught N square into I into A into L. Here I am substituting that, so U is equal to mu naught N square I A L into just wait, L is equal to, sorry, I will not be there, mu naught A into L. So this is mu naught, this is N square A L into this I square divided by what? 2. Is it? So now what I am doing here, actually I am multiplying by here, so mu naught N square I square A into L divided by 2 mu naught into mu naught. This is what? Mu naught square N square I square. This term can be written as what? This is equal to B square into A into L divided by 2 mu naught. And what is this? This is volume of the coil. So this is B square by 2 mu naught into volume. This implies, we write here small u, that is energy divided by volume. We write energy density, and which comes out to be B square by 2 mu naught. This is also called magnetic energy density. In electrostatic, or basically in capacitor, you must have studied that between the plates of the capacitor there is electric field. Electric field means some energy is stored. The energy stored, energy density, is half epsilon naught into E square. Exactly in same manner, inside the coil, is it, or solenoid, when the current is flowing, then inside the solenoid some magnetic field is there. So magnetic field also stores some energy. And what is the energy density, energy per unit volume in magnetic field? That we can express, it's B square by 2 mu naught, where B is the magnitude of magnetic field, mu naught is the permeability of free space. So this is energy density, and we can see here inductor store energy, and that is total energy is given by half Li square. Energy density, how inductor is storing? In the form of magnetic field, just like your EM wave has oscillating electric and magnetic field, so that also store energy in the form of electric and magnetic field. Exactly here we can see this inductor coil also store energy inside, because there is magnetic field between the coil, or you can say inside the coil, and there it's storing energy. So I hope it should be clear. That is the energy stored in inductor. So inductor is an energy storing device. Okay, so see next problem here. Like this problem is easy, but I want to tell you something like that is very important. Let me first explain this problem with the simple method that we have seen with the circuit analysis. Okay, so in the figure shown, initially there was no current, and at t is equal to 0 switch is closed, so switch is open and no battery, nothing is there. So initially current in the every part of the circuit is 0. At t is equal to 0, this switch is closed. Now this is the circuit. Now you are asked to find the current through the inductor as function of time. So this is the problem. So the basic approach for solving this type of problem is, let's say current I1 is flowing from the battery, and it's passing I from here, then it will be I1 minus I current through this resistor. The basic approach is apply KVL. So apply KVL, and this is the situation at time t, is it? And before that, let the current through battery is I1 at time t, and I across the inductor, so on. So now I can apply KVL. So let me write it in this loop 1. So in loop 1, you just listen it carefully, right? So in loop 1, from here I can write E minus, it's I1 into R minus I1 minus I multiplied by 2R equal to 0. Simplifying it, E minus, this is 2I1R plus 2, it will be 3I1R plus 2IR equal to 0. This implies I1 is equal to E plus 2IR divided by 3R. Okay, this relation, let me write it equation 1. Similarly, I can consider another loop this way. So let's say this is loop 2. Again apply KVL in loop 2. Then again I can go from here. So it's E minus across this I1 into R, and then this loop, then minus L di by dt equal to 0. Clear? I1 value I can substitute from here. So this is E minus R multiplied by I1 is E plus 2IR divided by 3R minus L di by dt equal to 0. R gets cancelled. This is E minus E by 3 and minus 2IR by 3 and minus, I can take it this side, so L di by dt. Clear? This can be E minus E by 3, it will be 2E by 3, and this will be 2E by 3 minus 2IR by 3 equal to L di by dt, and this implies di by, I can take here, it's a 2 by 3 outside, and it's E minus IR equal to 2 by 3 into dt. Rearranging it, we are getting this from 0 to t, and here it's 0 to I current, because initially at t is equal to 0, current in the inductor is 0. So integrating it, it's minus 1 upon R ln E minus IR, and if I substitute the limit, then it will be 0, then it's E equal to 2t by 3L R, and multiplying, dividing E minus IR equal to E into E raised to power minus 2t by 2tr by 3L, and this implies I is equal to E divided by R 1 minus E raised to power minus 2RT by 3L. So this is the answer we are getting. The important thing here is that this is very simple problem, and this way we are able to solve it and we are getting answer. But there comes sometimes like very complex problem situation. Let me write here, if I am adding here one resistor here and maybe one resistor here, and is it so some another situation may be there. In that situation, if you are going this way, you will get definitely answer, but this approach is very lengthy. You will consume a lot of time. Maybe in some situation you will have like 3-4 equations, and solving those it take a lot of time actually. So to reduce the time, we have something important for you, something like very interesting for you, and that there is one shortcut method to solve such type of problem, and that method I hope you have already studied in capacitor, even if you have not studied, no problem, I am telling you it from the beginning, just learn it. That will help you in solving this problem in just one step actually. So let me first tell you the approach, how it works, and then we will apply it directly. Okay, so this is the one approach. I hope you are clear with this. Now I am going to tell you another shortcut method through this problem, so you learn the method. Okay, so let me first erase this part. You remember this answer. I will show you same answer with another approach. So let me write it here. So E divided by R, and it's 1 minus e raised to power minus 2 RT by 3L. So this is the answer, and let me get it from different method. Okay, so let me explain you the method. The steps are same for every case. Problem will change, answer will change, condition, the way we will be dealing, exactly everything will remain same. Okay, so that is shortcut method. I'm telling you, I'm trying to explain you. Definitely it will take a lot of some time to make you understand the final step. If you understood the approach, then it will be just one step problem, is it? So let you please pay attention, focus on it and clearly, then it will be clear to you and you will love it, you will enjoy it. Okay, so let me tell you. So what is our idea, what is the motive behind this? We want to convert this system into some equivalent, let's say some battery E, some resistance R, and this inductor, let's say this inductor will remain L, it's some R, I can write E equivalent, and this is E equivalent. So if you are having this circuit and here this switch, and which is closed at t is equal to 0, I think for this circuit I can directly write my current I is E equivalent divided by R equivalent, and 1 minus e raised to power R equivalent into T divided by L. This will be the, so once you have this circuit directly, because we have derived the relation for this and it comes in this form, and we can directly write the answer. So the point is how we can convert a complex circuit into this circuit. Getting it? This is my motive, this is my objective. This is also still simple. I'm trying to explain you with a simple example. I will also explain once complex, otherwise you can solve it from like a book. You will find some little bit complex. Approach will work very easily and you will get answer within few seconds. Okay, so you got the objective. We are trying to convert this situation into this way, right? So we need here EMF is E, we need something E equivalent. Here our resistance R, 2R, and we need some R equivalent. So how we find E equivalent, how we find R equivalent, that is the point, right? I am telling you the steps to, so steps to calculate R equivalent or effective resistance. So what is this method? So for this, follow these steps properly. If you are not following it, definitely you will get wrong answer. Remember that. You need to remember steps are easy, not complex. One is short circuit the battery. Second step, open circuit inductor. Third is find R equivalent across the open circuit inductor. Now let me tell you what it means. This is our original circuit. Short circuit the battery. Short circuit the battery means remove the battery, place a wire. That is short circuit. Or you can say place conductor. If you I'm connecting it with a conductor, then that is short circuit battery. So battery will not be there. So after following this, battery is removed, short circuit. Resistance R is still there. Resistance 2R still there. 2R R. Inductor open circuit. So after short circuit the battery, open circuit inductor, find R equivalent across open circuit inductor. Now R equivalent across this is what? R and 2R in parallel, and then R equivalent is coming out to be 1 by, you can write these two in parallel, so it will be 2R by 3. R1 into R2 divided by R1 plus R2, and that will be, so this is your R equivalent. Is that clear? Opens short circuit battery, whatever, that doesn't matter how complex the circuit is, you will get within seconds answers. Okay, so approach is exactly this: short circuit this battery, short circuit resistance, leave it as it is, open circuit the inductor, open circuit the inductor. Now calculate R equivalent across the ends of inductor, and this is like, you can see series parallel combination, two resistance in parallel, and we are getting R equivalent 2R by 3. So we got one, that is R equivalent. Next step is, let me write B, and this is step A. Calculate E equivalent. This is next step. For this, what we need to do is just find the potential difference across open circuit inductor. Remaining circuit keep as it is. Find potential difference across open circuit inductor. Remaining part, just keep it as it is, means battery as it is, resistor, and this open circuit inductor. So this is 2R, R, and battery. Clear? Now you can see this is open circuit, so definitely there will be no current in this circuit. Current will be flowing this way. So current I can write I is equal to what? E divided by 3R. The potential difference across this resistor will be potential difference across inductor. So potential difference across inductor is equal to E equivalent, and that is given by I, E by 3R multiplied by 2R, that is 2E by 3R, 2E by 3. So we got E equivalent. Clear? So now this circuit can be reduced to this way, and that is equivalent to E equivalent, this R equivalent, and inductor. So how much? This is R equivalent 2R by 3, 2E by 3, and this is L. Substitute everything here. I is coming out to be 2E by 3 divided by R equivalent 2R by 3, 1 minus E power minus R equivalent 2R by 3 into T divided by L. This gone. I is coming out to be E divided by R, 1 minus E raised to power minus 2 RT by 3L. And now you can check the answer. We are getting exactly same answer. This is the method, approach, why and how it works. I hope you are clear with this. And you can see here, we don't have to solve much equation, no equation, simple like things. These steps will be like easy always. It will not be very much complex. Yeah, sometimes little bit maybe lengthy, but not definitely much complex. This overall method is much easier than that earlier method of solving equation. Let me tell you again, whatever the complex circuit is here, our objective is to convert this circuit into this form. For converting this circuit in this form, we need R equivalent and E equivalent. L will be just as it is, whatever it was there. So the point is how we calculate R equivalent, how we calculate E equivalent. There is proper step-by-step method to calculate R equivalent. To calculate, even like here you can see there is one battery. Even when there are 2, 3, 4 battery, doesn't matter. We will short circuit all the battery. Is it? So short circuit, you can write all the batteries. Is it? If it is 1, then it's 1 battery. If it is more, then you will short circuit all the batteries. Open circuit inductor. Yes, this situation will not work if you have more than one inductor. Remember that. In that situation, this will not work. We have to go with the exactly that method of lengthy solving equation. This will work only when we have one inductor, right? Okay, so or otherwise some inductor series parallel combinations are given and then you are asked to find the net current through the battery, then maybe it will work, otherwise not. Okay, and series parallel combination of inductor we will see after some time. Alright, so let me short circuit all the batteries, open circuit inductor, and find R equivalent of the circuit. We got this. Calculating E equivalent, find potential difference across open circuit inductor. Keep the circuit as it is and get the potential difference across inductor. That will be your E equivalent. Get the I in potential difference, whatever you can get, and then this circuit equal to this, and we can substitute the values here and we will be getting the answer directly, straightforward. So I hope you are clear with this approach. Learn it, it's very important. I'm telling you, it's going to help you a lot. I hope you understood. Let me solve few more cases based on this approach. Okay, see another application. So for the circuit given below, switch is closed at t is equal to 0, and this is the switch closed at t equal to 0, and initially there was no current in any part, and find the current through the inductor as function of time. So I am going to solve it directly only with the shortcut method. So I'm still explaining you again the approach. So first we need to find R equivalent. What is the approach? Short circuit, open circuit. So our circuit will looks like this 4 ohm and this inductor gone. This is, so it's basically 3 ohm, 4 ohm and 6 ohm. So here you can see across this, these two are in parallel. So parallel, then it's 4 into 6 divided by 10, 2.4, and 3 in series. So I can write R equivalent is directly coming out to be 5.4 ohm. Clear? Next step is getting E equivalent. For E equivalent, what we will do? Again this, and we will keep the battery. So in this situation, the circuit will become this battery, resistor, this resistor, open circuit, inductor, this and this. Now see here, 3 ohm, 6 ohm, 4 ohm, 20 volt. Is there any current flowing across this arm? It's definitely no, it's 0 now in this situation. So current will be only flowing in this way. So total resistance is 10, voltage 20. So current through the inductor like this arm will be like how much? 2 ampere. And potential difference across this will be, because across this there is no current, so across this potential difference will be 0. So potential difference across these two ends is potential difference across this end, and that is equal to I, that is 2 multiplied by 6R. So I can write E equivalent is equal to 6 multiplied by 2, that is 12 volt. Now this circuit I can directly write is equivalent to what? It's one battery, R equivalent, inductor. R equivalent 5.4 ohm, 12 volt, 2 Henry. I is coming out to be E by R, 1 minus R equivalent T by L equivalent. I is equal to 12 by 5.4, 1 minus e raised to power 5.4 into T divided by 2, and this is your answer. So you can see it's again very easy. If you go with this problem like with the traditional normal method of forming equation, definitely it will take a lot of time compared to this method. So I hope you like it. Try some more problem based on it. Let's see next part on this. Okay, so the next topic is mutual inductance. Up to now we talked about self-inductance and we simply call that inductance. So there the situation was, in one coil there is current. Due to that current, in same coil there is some flux linked, and whenever some current in that same coil is changing, flux linked to same coil also changes, and that same coil try to oppose that change in flux, and this property we measure in terms of self-inductance. Here mutual inductance is something different, like property is same, but it's defined for two coil or a pair of coil. So what is here happening here? Let's consider we have coil 1 and coil 2. Current in this coil 1 is I1 and current in this coil is I2. So what is happening like in this situation? If they are placed like this, due to this coil there will be magnetic field in this coil, and these field lines will pass through this coil 2. So the magnetic field lines of coil 1 will pass through the coil 2 also. You can see it here. So these are magnetic field lines. Because of current in coil 1, they are passing through coil 2 also. So when current in the coil 1 is flowing, there is also some flux linked to coil 2. Clear? And now you can see, so I can write this flux in coil 2 due to current in coil 1 will be what? Proportional to current in coil 1. Because if I am increasing the current in coil 1, more magnetic field will be there, more magnetic field lines will be there, and more magnetic field lines are passing through here, means more flux will be there in coil 2 due to current in coil 1, and vice versa. Means similarly, if there is some, let's say, current in coil 2, okay, so because of that there is some magnetic field lines in this coil. These field lines will be also linked to coil 1 also. So let's say blue magnetic field lines are due to current in coil 2, then you can see these field lines are also linked to coil 1. So I can also say that whenever there is some current in coil 2, the flux due to this current will also linked to coil 1. Understanding? So this is basically mutual interaction. In one coil current is flowing, and because of that flux is linked to another coil. Getting it? So exactly in same manner here also I can say, if I am changing or increasing this current, these blue magnetic field lines will also increase, because magnetic field in coil 2 will increase. Blue magnetic field lines will increase, means more magnetic field lines will be linked to coil 1, and I can say flux in coil 1 due to current in coil 2 will be also proportional to current 2 or current in coil 2. So here we can see the flux linked in one coil is depending on the current in another coil. Understanding? This is the flux due to other coil only. Here total flux I will write will be having its own contribution, and another is flux due to the next point, next coil also. Getting it? So the point here is that when current in coil 1 is passing, there will be flux linked to coil 2 due to current in coil 1, right? And I can write, let me write this phi 2 1. This is the flux linked to coil 2 due to current in coil 1. And vice versa, if I say phi 1 2, that means flux linked to coil 1 due to current in coil 2. Okay, so what I can say, this is the flux, which one? This is the flux through coil 2 because of current in coil 1. So definitely I can write phi 2 1 will be proportional to what? I1, and phi 1 2 will be proportional to I2. Flux in coil 1 due to current in coil 2 will be definitely proportional to I2. If I am increasing this, magnetic field strength in this will increase, magnetic field lines will increase, and because of this, flux linked to coil 1 will also increase. Getting it? And this proportionality, if I am removing, then I am getting here phi 1 2 1 is proportionality is removed by M21 into I1. And similarly, here I can write phi 1 2 is equal to M12 into I2. I will show you exactly even with the calculation. This M21 and M12 is actually equal. Sometimes like it's 0 also, that depends on how coils are coupled. But this I will prove this M21 is actually equal to M12 and we write it simply M, and this is called mutual inductance. Right, so mutual inductance, I can say it is a property of pair of coil. Mutual inductance I can define it is a property of pair of coil. Let me just okay, so mutual inductance, it is a property of pair of coil by which flux linked it opposes, by which it opposes the flux linked to coil 1 due to current in coil 2 and coil C coil side. Similarly, it is the property of pair of coil by which it opposes the flux linked to coil 2 due to current in coil 1, and that is called mutual inductance. It is denoted by M. It is also a geometrical parameter, or you can write depends on geometrical property. Remember that here flux linked in coil 1 is definitely depending on flux linked current in coil 2, but mutual inductance does not depend still on current. It depends on geometrical parameter, geometrical arrangement of coils. Is it like here in this situation there is some mutual inductance. If I am keeping one coil, let's say this way, and if I am keeping another coil this way, here you can say there is no flux of this coil is passing through this coil. So in this situation, as no flux of one coil is linked to other, so that's why there will be no mutual inductance. Means if there is any current in this coil, no flux is linked to this coil, so there will be no opposition by this, even when there is some change. So in this situation, I can write mutual inductance in this way. So mutual inductance depends on, you can write geometrical parameters and how the coils are arranged based on that also. It is not depending on current, and that's all basically. So this is your mutual inductance. So if like this is the flux in coil 1 due to current in coil 2, this is the flux in coil 2 due to current in coil 1. So when there is also current in coil 1 and current in coil 2, the net flux, is it? So when I am writing, when current is there in both the coils, right? Then let's say this is the situation, same exactly, and M is the mutual inductance of these pair of coil. Then phi 1, it is a net flux through coil 1. This phi 1 can be written as basically, one is flux a link to coil 1 due to current in coil 1, that I can write it's L1 I1 plus there is another mutual. This is M and I2, and this plus minus will depend actually on polarity. If they are magnetic field north pole, south pole, north pole, south pole, the flux will be additive. There is possibility that it is having north pole, south pole, and this is having north pole and south pole. So the flux of this will oppose or will be like cancelling out. In that situation, there will be negative sign. I will tell you when it will be considered positive, when it will be taken as negative also. Okay, so this can be plus minus. Similarly, I can write phi 2 is the net flux through coil 2. This will be L2 I2 plus minus M into I1. So these are flux or net flux through coil 1 and coil 2, including flux due to current in this coil itself, in this coil, and flux due to the current in other coil. So this is the flux due to current in other coil, and so on. Plus minus, I will tell you when we have one dot convention. With the help of that, we can define whether there will be plus or there will be minus. So okay, let's calculate mutual inductance of pair of solenoid placed coaxially. So here we have a situation how two solenoids are placed. So we have two solenoids, one is placed inside and another is placed outside, blue and red, two solenoids. If you look at it from this side, it will be appearing like this. Another one solenoid completely inside, coaxially both, another solenoid. The data area of cross section of the outer one is A2, number of turns per unit length N2, and its length is, let's say, L2. Similarly, for inner coil, I can write area of cross section is A1, number of turns per unit length N1, and let's say length is L1, and the current flowing in both of them, let's say it's I1 and here it's I2. Is it clear? We can consider either one. So now we need to calculate the mutual inductance of these pair of coils. Let's see how to calculate that. Okay, so the method is we will go either way. That's it. We can calculate flux due to the coil, inner coil. We can calculate the flux due to the outer coil also. Means current in coil 1 and flux linked to another coil. So let's consider current I1 in inner coil or coil 1. Right. So then what I can write, V is equal to what? Mu naught into N1 into I1. This is the magnetic field inside coil 1, and remember that this magnetic field will be only in which region? This will be only inside this region, inside region of coil 1. Inside region of coil 1. There will be no field due to current in coil 1 in this region. Means when current in this coil 1 is there, there is no field in this region. You must be knowing that. So this is the field. Now flux linked to coil 2 due to current in coil 1. So flux linked to coil 2 due to current in coil 1. So this I can write field will be also only in this region. So flux will be also in this area only. There are N2 length, N2 number of turns, and L2 like per unit length. L2 is the length. So total number of turns in coil 2 is N2 L2. So I can write coil, so per turn, that is V1 into area A1, and through all turns I can write phi 2 due to current in this comes out to be what? V1 into A1 into N2 into L. Clear? Because when current is in coil 1, there is only flux or magnetic field in this region. There is no magnetic field in this region. So that's why through one turn I can write magnetic field into its area of cross section, total number of turns, and 2 L2, so this is the total flux. And this I can calculate as mu naught N1 I1 A1 N2 N2, and this is equal to mu naught N1 N2 A1 L1 into I1. If I compare phi to 1 directly proportional to this is M into I1, this implies M is equal to mu naught N1 N2 A1 L1. This is the mutual inductance of pair of solenoid placed coaxially. Okay, so this is mutual inductance. We can get even this by considering the current in coil 2 or current in coil outer coil. Approach simple. We consider the current in one coil, calculate magnetic field, check in which region it is there, calculate the linked magnetic flux, total magnetic flux, and total magnetic flux linked to another coil to current in one coil will be expressed as M into I. Just comparing these two terms, we are getting actually M, and that is mutual inductance. So this is mutual inductance to current in coil 1. Let me do the calculation part for mutual inductance by considering the current in coil 2. Then I will prove you exactly that mutual inductance is same, doesn't matter whether you are considering the current in coil 1 or current in coil 2. Okay, so remember this is the same data. I am just changing a little bit. That is, I am considering this time the current in coil 2. So let's consider current in coil 2. So then what I can write, V2 is equal to what? Mu naught N2 into I2. Remember, this magnetic field will be in this complete region. But because this coil is only having this much area, so flux linked to coil 2, flux linked to coil 1 due to current in coil 2. So per turn I can write this is what? V2 into area will be still A1 with to all turns. This comes out with V2 into how many turns are there? That is equal to right here. Okay, because just 1 second here. Either I need to take total number of total length equal, or if let's say this is having L1 length, is it? Then linked field flux will be only this much length, common length will be there. Is it? So here I need to take either lengths, both lengths same and same, or if not same, then common length will be the only length through which flux is linked. We will assume in the outside region there is no flux, that we will assume actually. So that we need to consider here. So let me write these lengths are equal, then I will be writing it this way. Is it? So this I can write V2 into A1 into total number of turns N1 into L. And this can be, this is the flux in coil 1 due to current in coil 2, and this V1 is mu naught into N2 into I2 into A1 N1 into L. And you can see this is what? M into I2. Comparing it, M is coming out to be mu naught N1 N2 A1 into L. And you can check it is exactly the same thing. Mu naught N1 N2 A1 into L. So you can see, doesn't matter through which coil you are considering the linked flux, the mutual inductance is same. So mutual inductance is same. So it's not for one coil, it's for pair of coils. Whether you are considering flux due to current in coil 1 through the coil 2, or you are considering flux through coil 1 due to current in coil 2, it will be still same. So this is mutual inductance. Remember this relation. So let's see some more cases that I will discuss in next class.